In this video we're going to look at one of the homework problems that a lot of people have been asking questions about. This is in Hypothesis Testing 2. I'll look at problem number 1 from my problem set. Let's look at the problem for just a few minutes. There's some kind of a hypothesis test going on here. Notice the things that we can pick up immediately. We know what the significance level is. There's the alpha right there. It's testing a claim that mu is less than 19. Now think about that for a minute. In every hypothesis test there are two hypotheses. One is the null hypothesis and the other is the alternative hypothesis. Let me find a pen that I like here. Okay. So which is this? Is this a null hypothesis or an alternative hypothesis? And the test, the way that you determine is that the null hypothesis always has an equal sign in it. This one does not. So that's an alternative hypothesis. Mu is less than 19. The alternative hypothesis tells us which kind of test we're doing. Whether it's a one-tailed test, a two-tailed test, if it's a one-tailed test, if it's a lower tail, or whether it's an upper tail. Because mu is less than 19, this is a one-tailed test, and it's a lower tail. The alternative hypothesis tells us that information. The null hypothesis is that mu is greater than or equal to 19. Now usually statisticians don't put the greater than in here, they just say that it's equal to. It's that hypothesis that mu is equal to 19 that we test. So somebody's going to be looking at some distribution, and it may or may not be assumed that that distribution is normally distributed. So these are some x's, and the null hypothesis is saying we're thinking that that mu is equal to 19. And then somebody's going to take a sample. The sample size in this case is 44. And they're going to look at the x bar that they get from that sample, the mean of the sample, because that's going to be kind of an approximation of this thing. The distribution of the sample means by the central limit theorem is normally distributed, and it would have the same mean as this one. The mean of the x bars is going to be 19. Okay, if that's what the alternative hypothesis is. So because we're looking at a one-tailed test, and we're looking at the lower tail, then we want to have down here the alpha of 0.05. That's what the area is down there. So we're very interested in that particular number. When we do our hypothesis testing, we'll take this sample of size 44, find the sample mean, and see where it ends up. If it ends up above here, up in this area, then we will fail to reject the null hypothesis. If it ends up down in this area, then we will reject the null hypothesis. Okay, so we're very interested in knowing what that particular number is. That's an easy number to find. We can do that on our calculator. If you remember, your calculator has an inverse norm. So let me put that here real quickly. I've already found it on the menu. Remember, it's in second distributions, and then you go down to this choice of inverse norm. The syntax for this particular command is that you need to tell it what 0.05, what the probability is, comma, tell it what the mean is, 19, and tell it what the standard deviation is. Oh, shoot. I don't know what the standard deviation is, do I? Let me come back to the problem and I'll come back to here. Assuming that the 44 values, the beta is the probability of a type 2 error. Oh, there it is. They told us that we knew what the population sample, what the population standard deviation is. The standard deviation of the population is 8. So by the central limit theorem, the standard deviation of the distribution of sample means is going to be 8 divided by the square root of n, which in this case is 44. Okay, so I'll be able to find this value right here. That's going to be the inverse norm of 0.25, this area to the left of the point. It's kind of like finding a percentile in a sense. 0.05, the probability, 19, and this is going to be 8 divided by the square root of 44. Close the parentheses on the square root and close the parentheses on the inverse norm. And that number is going to be a 17.0162. So this number right here is a 17.0162. Okay, that seems reasonable, doesn't it? This one is 19. This is over here somewhere. That's telling us what that value is. When we find our sample mean, if our sample mean ends up being bigger than 17 point, bigger than this number, then we fail to reject the null hypothesis. If our sample mean ends up here, then we will reject the null hypothesis. The question here, though, is what if the null hypothesis really was less than this? Okay, so what if the null hypothesis really was down here? In this case, it's down at 14. Okay, what if the sample mean, I mean the real mean, really was 14? Okay, then this distribution of sample means would look like this. Okay, so it's supposed to be that same curve over here. It doesn't look like I made it quite the right shape, but it's this curve is just going to be shifted over here with this same standard deviation. And the question is, what's the probability of this being wrong, but us still accepting this probability? So here's the idea. We want to know this area right here. Okay, that's beta, the probability of making a type 2 error if the real mean was 14. And so it's really less than the 19, but there's this probability that our x bar could end up in here, and that would mean that we would fail to reject the null hypothesis even though the real mean was less than that. Okay, so this part will be easy to find. We can do that with the calculator. It's just going to be, let me slide this over so I can write it down. It's going to be the normal CDF of this area. The syntax for a normal CDF is to tell what this lower value is. So this number will go first, comma, this ending value, which in this case is infinity, in a mean of 14, because we're working on this blue distribution, and a standard deviation of 8.44. Let me just enter that in the calculator and we can see what that is. Second distribution, the normal cumulative distribution function I'm interested in going from, remember, it's going to be this value here, 17.0162, 17.0162, comma, up to the end, second EE, 99. That means 10 to the 99th power. That's big enough that it's certainly, of course it isn't out to infinity, but it's out there far enough. In a mean of 14, remember that's what we're saying, suppose that the real mean really was 14, and so we're trying to find this area, and a standard deviation of 8 divided by the square root of 44. That would be the standard deviation of those sample means. And so that's beta, 0.00619. Equal to 0.00619 in my case. Okay, hope that helps. Good luck.